Have you ever wondered if everything you've been taught about gravity is in fact accurate? Let's talk about gravity, one of the most misunderstood concepts in physics, and an enigma that even the greatest minds have grappled with. For many, the concept of gravity is quite straightforward. A force that simply pulls everything down, right? Apples fall from trees, we stay grounded on Earth, all seemingly due to this invisible force pulling us down. But what if I told you that gravity isn't just a force that pulls, it's actually far more intriguing and complex. The true nature of gravity is about the bending and warping of something we call space-time. You see, space and time are not separate entities but are interconnected, forming a four-dimensional fabric that is warped by mass and energy. Imagine a trampoline. When you place a heavy ball in the middle, it sinks, distorting the flat surface. That's similar to how planets and stars warp space-time. Now, if you were to roll a smaller ball onto the trampoline, it would naturally move towards the heavier ball, not because it's being directly pulled, but because of the warped surface it's traveling on. This is a simplified way to visualize how gravity works in our universe, but of course it's not as straightforward as that. The warping of space-time is not easily observable in our daily lives, and so the misconception that gravity is solely a pulling force persists. Yet, this understanding of gravity as the warping of space-time is not just a fanciful idea, it's a concept deeply rooted in the realm of physics, specifically in Einstein's theory of relativity, which has been proven time and again through numerous experiments and observations. So, let's dive deeper and unravel the true nature of gravity, ready to challenge your understanding. Gravity, as we know it, is not just a force pulling us down. Let's delve into this further. Have you ever wondered why apples fall down from trees instead of floating up into the sky? Or why we don't simply float away when we jump off the ground? The answer most of us learned in school is gravity, but it's not the full picture. Now imagine, if you will, a trampoline. If you place a bowling ball in the center of this trampoline, it will create a dent or a curve, right? This is similar to how massive objects like the Earth distort space-time. The four-dimensional fabric of our universe, the curve or dent created by the bowling ball, is like the gravitational field produced by the Earth. Now, if you roll a marble on the trampoline, it will naturally roll towards the bowling ball, not because the bowling ball is pulling it, but because the trampoline's surface is curved towards the bowling ball. This is how Einstein's theory of general relativity describes gravity. It's not a pulling force, but a pushing force, a result of the curvature of space-time created by massive objects. The Earth isn't pulling us down. We're being pushed down by the curvature of space-time around the Earth. Think of space-time as a rubber sheet. If you put a massive object on this sheet, it will curve or dent. Now, if you place a smaller object near it, the smaller object will roll towards the larger one, not because of some invisible pulling force, but because of the curve created by the larger object. This might be a departure from the way we usually understand gravity, but it gives us a more accurate picture of how our universe works. It's like seeing the world in color after a lifetime of black and white. So, gravity isn't pulling us down, it's essentially the curvature of space-time pushing us down. Now, isn't that a fascinating twist to our understanding of the universe around us? Let's consider two famous examples: the apple falling from the tree and the moon orbiting the Earth. Now, at first glance, these two scenarios might appear as quite different. An apple falls straight down, while the moon remains in a steady orbit around our planet. But what if I told you that they are both in reality doing the same thing? They're both falling. Let's take a step back. Imagine throwing an apple. It arcs through the air and eventually falls back to the ground. Throw it harder, and it travels farther before it falls. Now, what if we could throw it so hard that as it falls towards Earth, Earth curves away beneath it? Essentially, the apple would be in a constant state of falling, but always missing the Earth. This is exactly what's happening with the moon. You see, the moon is essentially falling around the curve of space-time created by the Earth's mass, but it's also moving forward fast enough that it never hits the Earth. This is a perfect illustration of how mass curves space-time, causing what we perceive as gravity. The apple and the moon are both responding to the curvature of space-time caused by the Earth's mass. The apple falls straight down because that's the direction space-time is curved by the Earth's mass directly beneath it. The moon, on the other hand, is a bit farther away, where space-time is less sharply curved, so it follows a longer circular path, but it's still falling towards Earth. This is a fundamental concept in physics, yet it's often misunderstood or overlooked. It's the idea that gravity isn't so much a force pulling things together, but rather a curvature of space-time guiding the motion of objects. In essence, the moon is constantly falling towards Earth, but also moving forward fast enough to miss it. So the next time you gaze up at the moon in the night sky, remember it's not just hanging there, it's actually falling perpetually towards Earth. But you might wonder, what about Newton's law of universal gravitation? Well, that's an excellent point. It seems to contradict the concept of gravity as a curvature of space-time, doesn't it? But here's the interesting thing, Newton's laws aren't wrong. They're just not the whole story. Imagine Newton's laws as a map. If you're navigating a city, a regular map will do just fine. It gives you an approximate view of the city, and using it you can easily get from point A to point B. But if you zoom in, you'll see that the map doesn't include every nook and cranny, every pothole, or every crack in the sidewalk. Now, for most of your travels, you don't need to know these details. But suppose you're a tiny ant traversing the terrain. Those details would become extremely important, wouldn't they? Similarly, Newton's laws give us a good approximation of how gravity works under most conditions. They allow us to calculate the orbit of the moon, the paths of the planets, and even let us send rockets to Mars. But they don't account for every detail. When we delve into extreme conditions, such as near a black hole, Newton's laws start to break down. They can't explain the immense gravitational pull, the time dilation, or the event horizon. This is where Einstein's theory of general relativity comes in. It fills in the gaps, providing a more complete picture of gravity. It tells us that gravity isn't just a force pulling objects together, but a warping of space-time caused by mass and energy. Newton's laws are like the map, a useful tool for navigating the universe, but Einstein's theory is more like a high-resolution satellite image, giving us a more detailed and accurate view. So while Newton's laws serve us well on Earth, they're just an approximation of the fuller picture painted by general relativity. So, have we been wrong about gravity all this time? To answer this, let's take a quick dive back into the heart of our discussion. We began with the intriguing misconception that gravity is a force pulling us down. This belief, while intuitive, oversimplifies the true nature of gravity. It's not a mysterious force reaching out from the Earth, but rather a consequence of how mass warps the fabric of space-time. We traced our steps back to the groundbreaking insights of Sir Isaac Newton and his apple, to the moon orbiting our Earth. Newton's laws of motion and universal gravitation indeed revolutionized our understanding of the physical world. But they left unanswered questions, inconsistencies that couldn't be reconciled with the growing body of observations and experimental evidence. Enter Albert Einstein. His theory of general relativity provided a radical new perspective. It depicted gravity not as a force, but as the warping of space and time by mass and energy. Picture a rubber sheet stretched out with a heavy ball placed on it. The ball causes the sheet to dip, creating a curvature. This is what mass does to space-time. It's this curvature that guides the paths of planets, of light, and yes, the apple falling from the tree. We also examined the counter-arguments, the challenges to Einstein's theory. But even after more than a century, general relativity has withstood the test of time, emerging victorious from countless experimental confirmations. So, were we wrong about gravity? In a way, yes. But every step, every misconception, and every correction has been a part of the journey, a testament to the human quest for understanding. Now, the next time someone speaks of gravity as a force pulling us down, you can enlighten them with the fascinating truth of space-time curvature. Stay curious and keep questioning.